Okay, so this is where we finished off yesterday. We had talked about just briefly, and I'm sorry that that image is kind of small, but you can check that in your notes afterwards. The image actually shows input, output, and processing, and the processor is divided into, well, we got three different components there. One component is sort of separate from the CPU, which is our memory. Actually, the CPU does contain some memory in the CPU, which are called registers, but then there's then some memory associated with it, and then there's our main memory, which is beside that as well, our random access memory. But so we've got memory, and we can just say, well, that's generic memory. Could be any of those. Could be our registries, or it could be outside. But the central processing unit has these two very important functions. Well, I guess you could say memory is a function, but one is it has to control the process completely, what resources are going to be used, what's going to be done next, and the other, it has to be able to do these mathematical and comparison, sorting, etc. functions in the arithmetic logic unit. And so we have some input, have some output. If you looked at this in economic terms, if you're looking at it from the point of view of an accountant or a businessman, you could look at this in that way, and you'd say, okay, I have inputs, that's like raw materials, that has a certain value, and then I have outputs, which are my finished product, which has a better value. And so we're prepared to spend some money or resources or time or power of some kind to do some kind of conversion of the inputs into outputs. And that's what we do. I mean, all of our computer processing, we're adding value to our inputs. We bring in inputs, we add some value to them, and we output them. So for example, of adding value would be, you could have an unsorted list of 1 million people, all the people that did something in Qatar. I don't know, maybe on an Etras app. And then you could sort them by alphabetical number on their names. Then that sorted list would have a higher value, right? Now that would require processing in the central processing unit. The arithmetic logic unit would do a sort. Given a algorithm, which was translated into a programming language, which would then do that sort for you. Yeah, and of course, that's a very, very simple example. Sorts are really actually quite important. That's a very simple example. And of course, there's many more things that we do with that data. Okay, we got the names of all the people in Qatar on our list. Okay, these people have traveled recently. These people had these injections. These people were in contact with those people. I mean, you could see that there's a lot of really good information that we could get out of that basic stuff if we could do the processing on it. And of course, we have computer systems that are doing that right now, as we speak, I suppose you could say. So we talked about Van Neumann. Van Neumann came up with that, that model of computer processing, yes? What is the algorithm that we should write? The very first programs, is that what you mean? Okay, so the very first programs would have been in these languages, like in our notes, it refers to AO, which I think is related to assembler language. An assembler language, we saw a little bit of example of it. This, I believe, is assembler language. And so assembler language, you have to specifically say what is where the data is that you want to use, and then you have to say what you're going to do with it. And so this little bit of code here, which is just basically adding two values together. Nowadays, like you say, all we'd have to do is say A plus B equals C. We'd have to declare the variable A, the variable C. It's very sort of intuitive. And we have computer programs like Excel, which are easier still, right? You put a number there, you put a number there, you put an equal sign in this cell, and then you click on that cell, and then you click on that cell. So that's where we've gone to. But I think your question leads to the fact that you're starting to understand that there's a lot of programming underneath that. We're doing this thing which seems very simple. You know, we've got our Excel sheet up and we see that number there and that number there, and we click on this and we say equal to that and that, and we're a programmer, right? Well, actually, somebody did a lot of programming to make that possible. And somewhere there's an assembler code that's underneath. The people who wrote the Excel program, they had to write stuff like this. Well, they did it in C programming language, which is a level above this still. So we talked about we haven't talked about it, but in the history of computing, we talk about generations of computer languages. And, you know, first generation computer languages was sort of using plugs, moving little interruptions around on your computer. So it was hardwire computing. As second generation programming language was this, where you are addressing individual memory sites. You have very simple code to say what to do with it. And those programs, we only have simple tools to use. So the programs were really long and really hard to read, because look, we got things like jump 7 bytes. You know, I mean, you're jumping from one part of code to another. People used to call it spaghetti code. And now we have much better, more structured programming languages to work with. That was the third generation programming languages. Third generation of programming languages was languages like C programming, Fortran, Pascal, etc. Now, those programming languages were procedural, and COBOL is mentioned here. Those were procedural programming languages, and so you didn't have to actually address the different components of the computer. So you might say, well, how did that happen then? Well, what we actually did is we went and we wrote operating systems. So the operating systems would take instructions from our third generation programming language, and they would do that work. They had an input-output system built into them. So there's an operating system. You know, when you have a computer, you turn it on, and the first thing that you'll see if you buy a laptop which has been loaded with Microsoft Windows, an operating system. And so they've gone way past the operating system that I first used in computers. I showed you that with the command line interface. So they've given us this Gui interface, and so it's, you know, we're programming, right? All we're doing is clicking a mouse. Yeah, you can make a program that way. I mean, that's where we're going, to a point where people are doing things that are very visual. But somebody somewhere has written this, right? And then somebody else wrote a C program that sort of is able to sort of work with this. And then on top of that, we have our fourth generation programming languages, our object-oriented programming languages, visual programming languages. Yeah, I hope I answered your question. Okay. Hafsa.
Yeah, coming to object-oriented languages.
Coming to?
Object-oriented languages.
Coming to object-oriented languages.
Yeah, what distinguishes, would affect be visual as well as object-oriented, or?
I suppose so. I'm sorry that I'm just trying to think of the languages. So when I say visual, okay, so you could do stuff with HTML. HTML is a visual kind of a language. You're making websites and stuff like that, and you're using JavaScript with it. And you can have plugins into that, which will include Python programming or Java programming. So yeah, I mean, nowadays people use a lot of a mix. And so that's why actually at this college you'll be learning to use HTML. Now, people write programs to run on your mobile phone, HTML, right? So I mean, things tend to be moving to the cloud, and so the HTML is very, very helpful for that. But you know, to make it work properly, we have to have some interaction with our users that are, you know, connecting to the internet, and so we need things like Python. Python works that way, and JavaScript, PHP. I don't know if you've heard of that, but yeah, I mean, so PHP will work with your HTML. HTML is visual. It's all about pictures and you can put your movies in there. Yeah, you know, I mean, you can do all this stuff with it. I think that's where we might be going with that, right? I think. Now, the reason why I say that also is because so much of our powerful computing tools nowadays are residing on cloud servers. So you know, in some ways, we've kind of gone full circle. What I mean by that is like in the 1960s, 70s, it was mainframe computing, right? And then there was this big thing bringing in what they called mini computers, which were mini mainframes, right? Instead of something that took up a whole room, you had something that could sit in a corner, but it's still as big as the photocopier we got out there, right? And you could have, a few hundred users connected to it using different terminals. That was the way we went. And then in 1980, they introduced the personal computer, and businesses took up the personal computer. And of course, they had to network those personal computers to get them to get any power out of them. And now what we've got is we've got people. The problem with the network computer at a business is that the business had to invest a lot in infrastructure. They would have to have mini computers or mainframe computers somewhere and build a whole network out to them. And that was nice. It had a lot of security sort of features about it, because that's your computer, nobody else gets into it, it's your network. But what they've found is it's actually more cost effective now to, well, let's let Amazon or Google, let's let them build a huge server farm. We don't need to use the whole server farm, but we'll rent a bit of space and a bit of time on that server farm, and we'll run our systems on it. And so we have this idea of cloud computing. And the idea, cloud computing, all you need is a device that connects to the internet. That's all you need. And then you get developers. It could be your developers, or it could even be that you have people working for these companies like AWS that will provide a solution for you on their system. And then so I'm talking a lot, but to make this possible, so many things had to happen. We have to have the internet. It has to be secure. So that's why we have at this college, right? People want to learn about how to secure networks. I mean, you can't run a business here in Brisbane. We're not in Brisbane. I'm sorry, that was when I was in Australia. We're in Doha. You can't run a business here in Doha running off a server in Iceland over that line unless it's secure, right? So we've got all kinds of cryptography that works with that. And so we can secure that line. And what that means is one of the big blessings of the way that we've gone to our computing nowadays is we've got this idea of scaling. So what that means is you can have a small idea. It might be a big idea, but you start off with a small system and you can test it out on the server, and it can grow quickly because they've got all that infrastructure there. You don't have to bring in 500 computer technicians into your business and buy buildings and put lots of mainframe computers in there. Somebody's already done that for you out in Ireland or Iceland, and you just plug into it. Anyway, so we're going to talk a bit about that in the next set of slides when we talk about computing nowadays, and we'll talk about some things like Internet of Things. This idea of computers everywhere, and if you're going to have computers everywhere, they need to be connected. And if they need to be connected, they need to be secure. So, I mean, I want to connect to all my things, but I don't necessarily want you to connect to all my. I want you to connect to the things that I want you to connect to, but there's some things that I don't want anybody to connect to. You know what I mean? So I'm going to use Signal to talk to my friends in a totally encrypted sort of end-to-end connection, which we'll delete the contents of after a couple of days. Not because we're saying bad things, but because, because we know that 20 years from now, things may have changed. There may be new laws. The political climate could change. And hey, all that stuff's out there, right? And things could be bad. So, you have to keep some things private. And we all do that, right? And yeah, laws change. I mean, the laws changed in Qatar. I mean, it was never a good idea to go around with your camera and take photos of car accidents. That was never, ever a good idea. But, 10 years ago, you could have done that, and you could have sent that to a newspaper or something like that. If you do that now and put that on Facebook, the police will come and do something because that's against the law in Qatar. Yeah, you didn't know that? Well, don't do it. You cannot take photos of people's accidents and put them onto social media. You can do it with your accident, but not with other people's. Okay, so just things like that. People, there is law to protect people's privacy, and so that's right. Like you said, really, so You know, maybe you did that 5 years ago and it shows up on Facebook. I mean, you know, it could be bad. So, I mean, you know, you have to sort of protect your privacy a bit. I talked a lot about that anyway. So, yeah, we were talking, we kind of go through this kind of quickly, I suppose. This is just talking about that low-level programming language, the second generation programming languages like assembler. What's really good about assembler is it's lean to the point of being, you know, it is the most efficient use of the computer resource. And so I mentioned yesterday, if you wanted to run really fast programs, you had some engineering problem that required things to go as fast as possible. Well, what would you do? You'd get as fast as computers as you could get, and you would run assembler on them. So when I say fastest computers as you could get, you know, with the fastest processors and memory, et cetera, you'd do that. And so, for example, airlines with their booking systems. Probably also military applications would do that as well. And maybe some communications applications. So Dr. Grace Hopper, a very famous lady, she developed a programming language called COBOL. COBOL was one of the first programming languages that I used. So it was developed in the 1950s. COBOL is a very wordy language. You know, you actually, if you add two letters together, you'll say, you know, you'll say let X take the value of 100, let Y take the value of 200, let Z equal X add Y, you know. I mean, it's very, you can read it, but it's, in order to write a single program in COBOL, I think if you wanted to say hello world, you know, that's what we do whenever we learn a new language. We say, okay, let's see, what does it take to get hello world on the screen? To get COBOL hello world on the string, you got to have like 5 different divisions of the program. It's about 55 lines of code, you know, like a page to say hello world. Now try that in Python. What do you have to do in Python? Print hello world. That's it. And up it comes on the screen. So, I mean, Python is way beyond sort of COBOL in terms of user accessibility, you know, new guys learning how to do computing.
So, when I went through it yesterday, I looked the word debugging, and it says something to win. Caused the error. The last, I don't understand that.
All right, so the computer was electronic. Okay, so you got wires connecting various parts, right? So a moth could cause a short circuit. So if you have 2 wires that are supposed to be separate from each other and you put them together, you've done that on your car maybe, and sometimes fuses blow. So you could blow up those vacuum tubes. Okay, so a moth could fly in there, and you'll know the moth's gone in there because you'll see a, you know, and that's the moth blowing up, burning. It's a computer shortage. So if the electricity was able to go across the moth's body, well, it'll kill the moth and it'll burn it up, but it'll also maybe blow out, burn up some part of the computer.
But she fixed that problem, right?
Yeah, well, she'd go in and change the burned up component. It'd probably be a vacuum tube or something, replace it with a new one.
So she didn't sound even though the moth. Sounds like a cure, like even.
Yeah, so she would have to remove the bug, which is a moth. A moth is a bug. So a bug is like a broad term used for insects. And so to remove the bug and then replace the broken component. And so we still use that word now, but we refer to bugs. When we refer to bugs in computer programs, we've got 2 different types of bugs. You can have a bug which is going to be a syntax error. A syntax error is going to be a bug that stops the computer from running. The program won't run because it's not saying the things that the computer can understand. Another kind of bug that you could have would be a logic error. Those are harder because the computer runs and it's doing something. It's just not doing what you wanted it to do. Okay, and that's both of those bugs are probably, well, yeah, they're the error of the programmer. And so this is why, if you want to be a programmer, this is going to be one of your biggest challenges, is you have to be very sort of careful and you know, attention to detail, because misspelling, one little putting something in the wrong place at the wrong time, you know, this is going to cause your program to not do what you want it to do. And that's going to be a bug and yeah, cause a problem. Any what? Computer languages? Yeah. I don't know what's happening in the future, but what I would say is absolutely okay, so Bill Gates said that 640K of memory is all anybody's going to ever need on a personal computer, right? He said that in 1980 or something. 640K of memory. I can't see, and he's pretty smart. He's a lot smarter than I am. I wish I was as smart as Bill Gates, so he's pretty smart, and that's what he said in 1980. Nowadays, you got gigabytes of memory on a. So yeah, we can't really see. I can sort of see us just getting to the point where it's almost like we don't even notice that the computers are there. It's just there, kind of in the background, and that's going to be sort of empowering for people, I think, because people will just, I mean, kind of like the scientific movies, where we say, computer, do this, and we don't even, we're already at that, right? Alexis, call somebody. Alexis, order me a new cafe or something. It'll be just, we won't even have to think we're doing computing. It's just like, okay, we got this problem solving sort of thing all around us and we just use it.
I think all computer programs at that time was the highest technology that
Yeah.
Now we think there's nothing that can top what we're doing.
Yeah. All right. So
a few years you're gonna find that it got top.
Absolutely. So I mean, I'm spending way too much money on mobile phones. Here's my mobile phone. One thing I notice whenever I watch a movie, you watch a movie and 10 minutes into the movie, you can tell when the movie is made. There's maybe two ways you can tell, maybe by looking at the cars, but absolutely by looking at the phones, right? You see these things, and it's only like 15 years ago, and they got this sort of clamshell Motorola thing, right? And what has it got on it, right? You can send an SMS. Or just even 5 years ago, you'd look at the form factor of the phones, and they didn't have the beveled edges, and they were way, way less powerful. I mean, it's just happening so fast. And so, I mean, back in the early 2000s, what people were thinking was, well, what we see happening with the phones. Okay, the first mobile phone that I ever used when I was working in the telephone company, I thought it was so cool. They let me have this mobile phone. Man, I had to have a big bag to carry it around. The phone was this big, right? It's huge, but nobody had them. I was lucky I had it because I worked for the mobile phone company. I'm walking outside in Sydney and I called my wife, she was in Melbourne and I was in Sydney, and I'm like, hey, look, I can talk to you. I'm not at a phone box. I thought that was so cool. That was like, as I said, that was 1990. But what we saw happening through the 1990s is these phones got smaller and smaller and smaller. And people were saying, well, the end result is the phone will be so small, it'll just be on your watch. And they're nah, you won't have a phone on your watch. That'll never freaking happen. Oh yeah. I mean, anybody here got a phone on their watch? There's somebody in this class got the phone on their watch, Okay, well, maybe it's connected to their iPhone or something, but you can talk on your watch. So that's what they thought. But what we ended up with is it got small and then started getting big again. Well, why? Because it's not a phone. I mean, most of the stuff I use this for is not a phone. It's a computer that just happens to have a phone in it. And the phone is lost amongst all the other stuff, right? But that's what it is, a computer. This is where you watch your movies, right? And this is where you do a lot of stuff. I only said one thing, right? Oh, I feel bad about that. Yeah, I mean, yeah, it's so the use of this is different. And, maybe the next thing will be to get it smaller. I mean, so Samsung's got this phone that folds out, right? So they got a screen that you can bend it. So maybe you can have one which, you pull the screen out of your watch or something like that. Who knows where it'll go, but it's a lot more stuff is going to change. And maybe you guys will be part of that. It's going to be kind of exciting. But a lot more stuff is going to change. Anyways, Grace Hopper did COBOL. COBOL was really a business programming language. So, you might say, why did the Navy have a business programming language? If you look at the way the Americans did their armed forces, it's a very businessy thing. I mean, certainly the way they prosecuted World War II and how they tried to prosecute the Vietnam War was very business oriented. What I mean is there were many very highly ranking soldiers from here to there. Logistics, big part of what they do, So buying things, making sure things are in the right place at the right time, following the chains. COBOL programming language is perfect for back in those days. So I think that might be why the Navy spent money developing that programming language. But that programming language was used by businesses, water companies, governments. Great programming language for a while there. Of course, it's been replaced by all this stuff nowadays. The integrated chip I mentioned a little bit yesterday. So these things look kind of like cockroaches. They actually, you can solder them into the motherboard or a circuit board on a computer or some other device. So that's what happens. And then inside the plastic, which is the insulator, is that silicon dioxide wafer chip, which has an integrated circuit on it. Some of these are really small. Some are kind of big, like the processor in your computer.
48 billion of the transistors make 1 gigabyte. I don't think that's true.
I don't know that it's not true, and I don't know that it's true. I'm sorry, I didn't write these notes. So there you go. There's a little bit of research that you could do, find out. I'm taking it on face value. I don't think they're going to lie to us, but I can't tell you if it's true or not. Sorry. Seems feasible to me. So a gigabyte is a billion. So what this is saying is that you'd need 48 transistors for every byte of, that's bytes, right? Gigabyte for every byte of memory. Now, a byte of memory is not the atomic or the smallest amount of memory. Smallest amount of memory is a bit. So a byte is actually at least 8 bits with whatever add-on bit things you got. So, I mean, so that's a factor of 8 or 10, but yeah, so 48, yeah. Yeah, all right. So you read ahead, right? Okay, so here's our units of memory. Now we talk about bytes like this, like gigabyte, but the actual way that those numbers are brought is using the base 2. So base 2 is 2 to the power of. So that's what we mean by this, 2 to the power of 10. So 2 to the power of 10 means 2 times 2 times 2, 10 twos. This is 2 to the power of, this is 2 to the power of 3, which is equal to 8. And so when we say a petabit is 2 to the power of 50, that just means 2 times 2 times 2 times 2 times 2, 50 times, right? And so that is this symbol means approximately equal to. It's approximately equal to 10. So if you convert from base 2 to base 10. So we do conversion of base 10 because that's the system that we've been using with our written mathematics for the last 2,000 years, I guess, is base 10. But computers use base 2. So we have to have some kind of, you're going to actually do this maybe in your math class, but you're going to do this, a little bit of this in this class, where we'll do some conversions between base 2 and base 10. As I said, computer uses base 2. But when we talk about it, we talk about it in base 10 because that's what we're more familiar with, right? So we can say, oh, that's 10 to the 15 means 10 with 15 zeros. That's billion. But we see that it's not actually 10 with 15 zeros. It's nearer to this other number, which is the actual number that you get when you do 10 times 10, 2 times 2, 2, 2, 2. You get the idea? So that's how that is. I'm sorry about that. It's just the fact that we don't use base 2 for our number system. The computer does. So we have to have some conversion between. All right. Moore we mentioned yesterday, and he was involved with Intel. Have you guys ever heard of Intel? Okay, where have you heard of Intel Hefsa? Intel produced the chips that were the processing chips for the first generations of home computer, desktop computers. So we had the 8088 chip. That was an Intel chip, and the 286 chip, and the 386, and the Pentium. And so basically, now if you looked on your laptop computer, it'll probably have a little symbol that says i7, which is Intel Generation 7. Okay, so yeah, or i9. That's that. Okay, so that chip was designed by Intel. Now, Intel used to make those chips in the United States because Intel's an American company, but I think now they might be getting them from Taiwan, or they might. Now, China, of course, is trying to push Taiwan out of that market because China wants Taiwan to be part of China. Well, China says that Taiwan is part of China, and Taiwan says, no, it's not. I've been to Taiwan, but I haven't been to China. But Taiwan's nice. You should go there sometime. But they, up until very recently, they were making like so many chips. I won't say, I can't say the most of the chips, because a lot of chips are also made in Malaysia, and some are made, I think, in Vietnam. But Taiwan was making a lot of these chips. And China is trying to get into that market now. Well, China's trying to get into every market, right? So the founder of Intel, this guy, he noticed. So that's what we mean by empirical. Empirical is a word that we use in science. It looks like a big word. Sounds like, oh yeah, that's a big word. Only big people would use that word, right? All it means is, if something is empirical, it means that we did an experiment to see if this was true, or we observed that this was true. If it's as opposed to theoretical. Theoretical was the mathematician sat down in a room in a corner and sort of calculated that this was true, right? Theoretical or calculated, as opposed to empirical. This is a fact. If it's empirical, it's a fact. We observed it is true. That's what we mean, as opposed to sitting in a room and coming up with a theory. This one we observed. He observed. So basically, he just noticed that, hey, you know what? Every 18 months to 2 years, the same amount of money will get me twice as much as computer power. And then he said, he published that, and it became known as Moore's Law. And it's been basically true since then. Now, we did come up against, it hasn't been a straight line like that. It's been a line where it goes up fast, then stays, then goes up fast. Because what happens is they meet a technical challenge, an engineering challenge, and then we have to solve that challenge, and then we speed up. And so we've had a technical challenge that's kind of stopped it there for a while, and that has been the heat produced by processor chips. And you might have noticed that. I think they're sort of getting over that, but we had a lot of sort of laptop failures and things in the 2000s where they're just producing so much heat. And so they basically limited the speed that they were going. Well, we're not going to go any faster until we solve this heat problem. And so they have to solve that. I mean, there's some theoretical, again, theoretical. There's a theoretical solution to it, but then we have to bring the engineers in to actually solve all the problems. And I guess that's the exciting thing about engineering is, whenever you go to solve something that seems theoretically simple, then you actually come to the real world and you have to find these. It's usually more than one little thing to get rid of. So there's the heat problem there. I mean, one of the theoretical solutions to that is, well, we could do distributed processing, where instead of having one processor do all the processing, we're going to have 10, so we can distribute all that heat out and then sort of have them interconnect. But one of the ones that I'm hoping will happen in the next 30 years, I don't know, is replace some electrical current for light. And the reason why I say that is because electricity, whenever it passes over a conducting, it's not, unless you have a perfectly conducting substance, and I don't know if there is such a thing, the electricity going through a substance always meets some resistance, and resistance causes heat. And you got a lot of those processors, there's a lot of electricity going through there really fast. That's a lot of heat. And that's kind of, yeah, they got to solve that problem. So yeah, they will, I'm sure. The GUI thing, we did talk about that yesterday. I vaguely remember this, circa 1984. Things were kind of sad. And a couple of years later, IBM did come out with their own operating system that they put on their own computers. They actually had their own, and for a couple of years, they got a bit of market, but Microsoft beat them. Pardon? Yes. So it's like your file manager. So these are like folders. And so it looks kind of like what you do, but this is like 1980. And yeah, this is pretty sad looking, isn't it? Windows 1. But then they went to Windows 3, and now what are we on? Windows 10. Yeah. So GUI was a great idea, and it's with us now. And so there's just a little bit of history. So some people would have these people as sort of like cultural icons, big heroes. But I mean, if you looked into them individually, I think you'd find that there's a lot not to admire about them. I mean, they're basically sort of, in Australia, we would call it sharp business practices. Other people would maybe call it sort of stealing, lying, and cheating. And so there was a lot of that going on. Bill Gates, he stole his operating system from some guys in Texas, I think. Wozniak, pretty smart guy. Jobs, I don't know. He was okay. It was kind of weird though. I mean, he was dying of cancer, and all he would do is drink wheatgrass or something like that, right? He wouldn't go and get proper treatment, so he died. I don't know who that guy is. I think that's the new CEO of Microsoft when he quit. What was his name? Paul Allen. Yeah. So when I say he quit, so you know that Microsoft is publicly traded. That is, you can buy shares in Microsoft, and so you can make a lot of money if you held the shares when they went up in price. And so Bill Gates, he owned a lot of the shares, and so he was able to just quit working at Microsoft and take the money. Sorry? He just lives off the shares. He at one point he was the richest man in the world, so he had plenty of money. Now the richest guy in the world, I think, is Elon Musk. But like last year, the richest guy in the world was Jeff Bezos. And imagine Jeff Bezos, he got divorced. He had to give his ex-wife half his money. He's still the richest guy in the world. Go figure. How much is enough? All right, so the mouse sort of developed from something that wasn't so great to something that you're more familiar with now. And what am I going to say about that? I mean, that's an engineering challenge, right? You move something over, the light. So you see nowadays, well, they had a roller back in the old days. Now we got a little laser light in there, right? And the light picks up whatever it's moving over and translates that to XY position. Now, this should be a new heading. Should actually be on another page, I think, because what's Ethernet got to do with mice? I don't know. I suppose it's something to do with the inputs and outputs thing, right? Yeah, so Ethernet. We are all connected to Ethernet here. If you have a cable like that that's connected to your computer, we call this cable Ethernet. Ethernet is just a standard, which is 8 wires. That connects to a special port in your computer. The walls here have all got that. All of these computers got Ethernet. These white cables, no, that's power. Now I'm just trying to look for the Ethernet cables on here, because isn't that for what? Faster than Wi-Fi, yeah. Okay, so Wi-Fi is getting pretty fast. I mean, we've gone through several generations of Wi-Fi, but Wi-Fi has a problem in that when two devices want to communicate through Wi-Fi, they have a lot of overhead. One has to say to the other one, "Are you ready to talk?" And he has to say, "Yeah, I'm ready." "Are you sure?" "Yeah." "Okay, now we can talk." Whereas with Ethernet, it's just straight through. So it is more efficient. The protocols are simpler. And so the internet actually started a long time ago, as it says there in 1962. That ARPANET was a American military project. That was taken up by some universities in the west of the United States. So that's like Seattle and Utah. But they started communicating between each other. And some guy wrote a program to do, this guy, Ray Tomlinson, to do email. And so that was kind of like the first thing. So university people were using it to send their talking to each other back in the 70s. And so internet properly got going in the 1980s. 1990, the first internet that I used was like 1990, and that was before Mosaic. And you might go, what's Mosaic? Well, Mosaic was the internet with HTML with a graphic user interface, because before that it was just like typing stuff. And it was kind of boring. Actually, they used to have these things called bulletin boards, and people go there and sort of type stuff. And the first ones that I connected to the internet in like 1990 in Australia, and I said, oh, let's see what's on there. And so I look around and find some bulletin boards. All the ones that I found were these ones in Singapore, and there's all people complaining about the government in Singapore. Oh, that's interesting. So that's what the internet's about, complaining about the government. Yeah, okay. Yeah, so then Mosaic came out in 1993, and what we got was this internet, which is where people could put things, pictures went up, and businesses started advertising, and news picked it up. And that was sort of Internet 1.0, which is where you could just put a static web page up. What I mean by static is it's there and people can look at it, but they can't really do anything with it. Now we have an internet which is not static. It's a dynamic internet. The actual page will change depending on the user interaction with it, right? You click on a button and a whole lot of different things happen. You can buy stuff. Okay, so that's only possible through what we call Web 2.0, the second sort of thing of the web, and that's only in the last 10, 15 years. And that requires, and maybe you guys will do this, you have to have JavaScript programming language. You have to have something that will interact with the user. So JavaScript has made that kind of possible. So we went from HTML to JavaScript. Google, they got going in like 1998. Very good idea. As I said before, that was all about sorting. They sorted all the records, and then they're available for you to sort of find them.
What do you think was going through the head of the people who created Google when they named it Backbone?
I have no idea. So the two people you're referring to, their names are here, Larry Page and Sergey Brin. What were they thinking? Okay, so it says here where they got the name Google from. That's like a mathematical word that means 1 with 100 zeros after it, to show that it's a really, really big number. I don't know why they would get back. I don't know. University students, right? They're young and they come up with all kinds of ideas. There's Bill Gates making his quote about nobody needs a computer with more than 640K RAM. That wasn't that long ago, 1981. And there's those two guys. They look kind of young there, right? They're like about you guys' age. So Stanford University in the United States, that's like near to San Francisco, in the area where they call Silicon Valley. The whole idea of Stanford University is we bring university students here, they have good ideas, and then we put them in contact with people who have money, and then they can make businesses. And that's how Silicon Valley really got going. Hewlett Packard, these guys were there, they had these ideas. We can sort all of these data out, we can sort it out, and we can filter it, and then we can give people results. That's basically what they did, and they came up with Google. And now they're like gazillionaires, right? Okay, so here it is. Why did they call it Backrub? Doesn't say, right? Just says why they call it Google, 100 zeros. Okay, and so there's some more history. You see it's all happening kind of fast. I'm not going to go through that. Yeah, I think YouTube belongs to one of them. Yeah, probably Google. Yeah, and like Facebook bought WhatsApp. Yeah.
And all the social media.
Yeah. Skype. Who on Skype? I don't know. No, Skype is Microsoft, isn't it? I can't remember. Anyway, Steve Jobs, really smart guy. I don't think he had a university degree. Just really smart guy. But you know what Steve Jobs was? His real thing was he liked art. He was artistic. But artistic guy who happens to be able to do things with computers. So that's why he thought they need to have an Apple, because he's looking at all these personal computers and they're so lame, right? You can't draw anything with them or anything. And so he put a big focus on the way that the computer worked, but not just that, the way the computer looked, right? So the Mac looked different, didn't look all sort of ugly like other computers, and even now. And so because of that, he could charge more money. So that was kind of good. There's Charles Babbage. We talked about him. made a mechanical computer. And Turing, guy who had a chaotic life, but made big strides in sort of cryptography. There's Grace Hopper, COBOL language, and Blaise Pascal, French dude. All right, so I'm going to stop there, and we will, in a second,